Okay, good afternoon, everyone. Thank you for joining us today. My name is Marissa Waterman, and I'm the Marketing Director here at the Academy. We're happy to be here today with Ryan Capel from Stantec. Ryan serves as the Minneapolis location leader for Stantec's water business line in Minneapolis. He's a professional engineer working in the area of water treatment for 25 years. Ryan has applied his education from University of Minnesota with a bachelor's in civil engineering, along with a master's degree in infrastructure systems engineering, to design and implement treatment solutions to help achieve drinking water compliance. Ryan will be discussing Pfas treatment for drinking water. Before we get started, I just want to mention that you'll be able to message your questions at the end of the presentation. Once the presentation's over, you'll be able to type in your question into the attendee chat on the left-hand side of your screen. We'll also share Ryan's email address so you can email him directly with additional questions you may have. Okay, let's get started. Good afternoon, Ryan. Thank you for joining us. We're ready when you are.
Great. Thank you, Marissa. And thank you to the American Academy of Environmental Engineers and Scientists. I'm happy to have this opportunity to talk with you over your lunch hour. Some of you may know my colleague, Joan Oppenheimer. She is a part of the team that I work with, and I'm proud to work with at Stantec. And our goal today is to talk with you about PFAS in drinking water, and particularly about solutions that keep municipalities in compliance. The key word here is compliance, because that means different things for different areas of the country, different states, different jurisdictions. And I think that today, after this presentation, at least it's my hope that you'll have a better understanding of those differences. So the agenda, I want to begin to go through, just give a little background on PFAS. Bear with me. I know we're coming from a lot of different perspectives. I would also ask that you understand that the perspectives we're sharing today are our view as of May 12th, 2021. This topic of PFAS is evolving and changing every day. And so just recognize that it's changing, and we're giving our best view of it as it stands today. So with that in mind, some of the treatment options that are available to municipalities today, we'll talk about. To make it a little more real, I'll bring in a case study for one of the communities we've worked with in Cottage Grove, Minnesota. And for your viewing today, you're fortunate we get to update you on some current status of a pilot study that's underway. So fresh off the press, with your admission today, you'll get some up-to-date information on the pilot study. And then we'll summarize the solutions that we talk about during the discussion and end with some questions in the discussion period. I do expect it to last about 50 minutes, so I'm hoping to give you your money's worth. All right. So let's talk about PFAS and where it is in the United States. This is a map that was put together by the Environmental Work Group. It shows areas where there's industrial and municipal PFAS contamination. This map kind of reminds me of the COVID-19 maps that we would see coming out of Johns Hopkins University about a year ago as cases were confirmed across the US. PFAS isn't quite as sinister as COVID, but it does remind me of those things. And the other similarity is those areas that tend to see, where you see dots on this map, are the areas where they've looked for PFAS more extensively. So maybe the thing to take from this map is that California and Michigan, New Jersey, some here in Minnesota, places where they've looked for PFAS, they do tend to find it. And with this, there's a lot of different perspectives on how to manage and regulate the presence of PFAS in the drinking water. So each of these states currently has their own viewpoint on how to regulate. And with that in mind, here's a map that shows the states in blue that have some form of guideline established. Not all states are participating beyond the US EPA guidance of 70 parts per trillion for the PFOS and PFOA substances. There are states that have gone out on their own and established their own MCLs. Those are the states in orange that you see here. So it's a very different enforcement of this topic depending on where you are. And there are a lot of reasons for that. There's differences in concentrations and differences in the types of substances that are found in different parts of the country, differences in the toxicology study and different things like that. There's also this PFAS and water cycle map that you're looking at here. This is put together by the folks in the Michigan in their Department of Environment. PFAS gets into our environment through all these different channels, from industry to landfills, leachates from the landfills. Sometimes the biosolids that are generated from a wastewater plant are spread across the land, and then that's a source for PFAS to get into the ground and into our water supply, whether it's surface water or groundwater. There are just a lot of factors, is the point of this chart. So more specifically, this is a graph, and it might be kind of hard to read. I've got the big red arrows focused on PFOS and PFOA because those are the two that the EPA has established 70 part per trillion combined guidance for. But you can see if it's clear on your screen, there's all these different states over here on the left. The ones that are up in the top area, those are the orange states on that previous map that have MCLs. There are other states like California that have non-MCLs, but they're in the kind of a pre-proposal stage. And then there's states like Minnesota that have guidance as well. But we're looking at, in Minnesota, 7 different substances. And I'll point out on this, if you can see it, Minnesota is one of the only states that has a guidance value for PFBA. That's a short chain PFAS substance. And you'll notice that number is very high compared to some of the others. It's 7,000 parts per trillion, or nanograms per liter. That'll come into play later in the presentation. Here's another way of looking at that same data. If you got EPA is established at 70 parts per trillion for PFOS and PFOA, you just see on the bar chart how some of these states are much, much lower than the 70. Others which aren't on the list, which Joan and I are working with the state of Illinois, they're proposing a limit as low as 2 nanograms per liter for PFOS and PFOA. So that 2 would compare to 70 established by the EPA. So a much different perspective depending on where you are. Next is this slide I created to try to sympathize with the challenges that utilities are facing. I like analogies, and so if you're a person who's lining up as a utility manager trying to provide water that's in compliance, which is the topic of this presentation, you're really trying to generate water that meets a certain standard. And if it's an analogy of this field goal kicker trying to hit a target, and we've got different targets out there, which we just showed, it's almost as if these goalposts are moving back and forth, or closer to you or further away as you're trying to kick. So I really sympathize with utilities. I even thought another analogy would be that it's almost like trying to kick a field goal while there's an earthquake going on. And then there isn't much margin for error. We're talking about parts per trillion, nanograms per liter. To put that in perspective, it's 1 drop of ink in 20 Olympic-sized pools. But toxicologists and epidemiologists are finding that just that small amount is enough to make a difference. It's not an easy feat, but the good news is there are solutions out there. And so I'm here to talk to you about a few of those. Currently, conventional drinking water treatment methods have almost no impact on PFAS. These are forever chemicals, is their nickname, and that's because they just are ubiquitous in the environment and somewhat in our bodies, and they don't break down. And so we need to explore solutions to give these utilities and water purveyors a chance against this issue. The lowest hanging fruit, the most available technologies today, as we see it, are activated carbon, anti-exchange resins, and high pressure membranes. And they've been proven, the good news is they've been proven to be able to remove about 95% of these substances. There's all kinds of factors that I mentioned earlier. We have background source issues. We have different concentrations, different footprints of these treatment technologies. So some sites may be able to accommodate treatment technologies, others may not. Lots of issues to consider when we're looking at options and solutions. So here's a little simple diagram of the three, what we're calling the three that are ready for prime time. GAC, so this is the treatment process is put together in a column, a downflow column where the water comes in from the water source, whether it's surface water or groundwater, and flows through the GAC column, and the permeate comes out the bottom. Same situation with ion exchange resin. When that's used as a sorbent, it's typically from the top to bottom flow. The other option that's out there is reverse osmosis or nano filtration membranes. And with that, we flow through the membrane and the permeate comes out the other end, free of PFAS essentially, but there's a reject stream. And the issue here is with this reject stream, we need to do something with that liquid continuously. The issue with GAC and ion exchange is the material goes through and the PFAS absorbs to the surfaces of the GAC and the IX and then eventually becomes exhausted, and we can then remove that GAC or that IX, ship it off to proper handling, and that can be processed appropriately. So a little closer look at the GAC. This is a picture of one of the interim treatment plants that we've installed, but essentially showing that same concept I was just going through, where the water comes in the top of these vessels and the effluent flows out treated from PFAS. But eventually that material, it has a finite life, if you will, and eventually the GAC material becomes exhausted, or all the surfaces become covered with PFAS. So the strengths of GAC is it's got a very long, good history of success. It's good at removing long chain compounds, or the 8 carbon chains like PFOS and PFOA. There are multiple suppliers. There's a lot of study on it. Essentially, it's a very well accepted treatment technology. The weaknesses are that it doesn't quite have the ability to do its job when there's high TOC. It doesn't do as well against short chain PFAS like the PFBA that I mentioned earlier. And there are some uncertainties as to what happens with this carbon once we do ship it off. The important feature of carbon is that we're looking at the empty bed contact time. And so there's, like I said, there's a finite amount of space on the surfaces of these granules that can receive PFAS. So the important part here is that the capacity is finite. Eventually, we're going to need to remove that media. And in fact, sometimes from the numbers that you'll see later, we're seeing that some of the material can get kicked off of the surfaces through the treatment process, and we actually end up with higher concentrations in the effluent. So we need to watch that with GAC and be very cognizant of the empty bed contact time. So another example is with GAC, I wanted to point out that we use a lead lag configuration. So there's a redundant filter, if you will, where we go through a lead filter and capture and test for the PFAS substances in the effluent. And then that effluent runs up to the lag filter and runs through a second course of media. That way there's a safety factor, if you will, that the Department of Health can observe and monitor that lead vessel to know if things are starting to break through before knowing that they have a lag vessel available. So like I said before, tried and true, it's a robust option out there for utilities to use. The other thing about it is with that understanding, and we know roughly or generally with a given water quality, how long the carbon can last. It's different, it's site specific, it's definitely specific to water quality and the different parameters like TOC and how much concentration we have. Like this graph shows concentration on the left and the bed volumes of throughput on the bottom. But over time, we can gain an understanding of what the breakthrough curve looks like, and we can start to predict how many bed volumes we're going to be able to get through a given water quality. So now I think we can move on and talk about ion exchange as another solution option. The strength for ion exchange, it's a little bit better on the short chain PFAS, which I can show you later. It's still effective on the longer chains. Um, the issue with TOC is a little bit less than that of GAC, and there are shorter empty bed contact times required for the same removal. What that means is we can pack this material into smaller vessels and in a smaller footprint. The weakness, and you'll see this firsthand results, is that there are some issues with complexing materials in the water, such as iron and manganese or other metals. And sometimes those can really cause a problem if we don't have pretreatment. There's for cleaning this, it's not a type of material that we can clean safely with drinking water. It's a one pass, for the most part, a one pass option. There are folks out there that are trying to generate regenerable ion exchange resins. And to give you a little picture here, like the other with GAC, we have water that comes in the top of these vessels, the effluent comes out the bottom, and eventually we will entirely remove the ion exchange resin and ship that off for processing. The next option is reverse osmosis or nano filtration. Strengths here is that it removes nearly all of the substances, 99%. There are multiple suppliers. The weaknesses are that there's limited disposal options. And like I said earlier, there's that consistent reject stream that we have to deal with. And that reject stream is going to contain PFAS. So now what do we do with that? There are companies, as we speak, everyone is working to develop technologies. And we know that there are super adsorbers out there that can receive that reject stream. And eventually those types of sorbents will become more commonplace, and we may be able to see reverse osmosis used more as a common treatment solution for PFAS. But as it stands right now, as far as our team is considered, the two lowest and most viable are GAC or ion exchange. I mentioned all the different folks out there developing. Everyone's trying to solve this issue and to design a better mousetrap, if you will. There are novel absorbents being considered, anything from coconut to different synthetics. We're looking at porous materials, oxidation systems, redox, ozofractionation, senolysis, and ultimately the holy grail would be is if we could find a technology that actually breaks the fluorine carbon bond. And that's something that is very difficult to do, but there is promise out there. I've observed systems myself at the academic level that are showing promise in being able to break that PFAS and destroy it. Just not ready for prime time as we speak. So when it comes to providing solutions, we want to help these communities that are in some cases a state of crisis. And one of those is Cottage Grove, Minnesota. And so this is where I want to try to give you a little real world example. A little background before we dive into Cottage Grove, Minnesota. Minnesota is the home of 3M, Minnesota Mining and Manufacturing, and that's a company that back in the 40s and 50s was generating these PFAS substances for different things, as you all maybe have heard, different things like stain-resistant carpets to the Teflon on your pots and pans. Wonderful innovations and great engineering took place, but now as we learn that it can cause health issues, we need some innovation to try to remove those substances from the ground. Already in 2002, we were finding health impacts, and the city of Oakdale in Minnesota had to go through and install treatment. Fast forward to 2017, the Minnesota Department of Health instituted what they're calling health-based values. This is kind of a precursor to health risk limits. The upshot is that when those limits were established, and that was based on toxicology testing and thorough analysis throughout the course of essentially from 2002 to 2017, the upshot is that 8 of Cottage Grove's 11 wells were beyond the health-based guideline. That pushed them, the city, into a situation where they had to either tell their residents that our water is non-compliant or take action. And they chose to do the latter. They chose to construct 2 interim treatment facilities. One of those is pictured on the upper right. And they decided to do it with haste. We helped them with the design and implementation of 2 facilities within 75 days, that's start to finish. And so they really, through that, were able to maintain the trust and confidence of their customers. It was before, so they went through that process before a settlement was reached with 3M. Just in February of 2018, the following year, a settlement was reached with 3M where they decided that it was appropriate to allot $850 million to 14 different communities to split that sum to resolve PFAS in the drinking water. It was after that settlement and just last summer that we realized PFAS concentrations were rising and we had to install a 3rd interim treatment facility. And so those interim facilities are now opportunities for us to learn a little bit more about PFAS in the groundwater in this case. So just to give you a visual of the issue in Minnesota here, the dark shaded areas are areas where PFAS was disposed, and the PFAS found its way into both surface water and groundwaters and made its way across a large portion of the southeast metropolitan area of Minneapolis and St. Paul, covering 150 square miles, impacting 8 municipal systems and 2,700 private wells. And so as that plume moved across the region, it found its way into both the Mississippi River and the St. Croix River, bounded on the south and on the east. Like I mentioned, this gives you, it's not a very clear picture, my apologies, but a large portion of the southeast metro is impacted by this, including 14 communities. So it's a real problem for the utilities in those areas. But the good news is, with those interim facilities that we installed, we found great success. We were able to get them all completely installed and closed in less than 90 days. The solutions were cost effective, essentially about $1 a gallon. So if we had 1 million gallons treated per day, it would be about $1 million facility. The water that we produced, and you'll see the results later, is compliant. Keyword again is compliant. And it set the stage and bought time for us to develop long-term solutions. Let's dig in a little more specifically. Where do we go from here? With those solutions in place, like I said, we have time, but we want long-term answers. And so the Minnesota Pollution Control Agency authorized a pilot study. So Joan and our team at Stantec have been able to work with the MPCA, the Department of Health, and the City of Cottage Grove to develop a study that would compare ion exchange resins directly to GAC and find out if, in the case of Minnesota, the only approved method is GAC treatment. So we want to see if IX could have the mustard to meet MDH's requirements as a treatment technology. And then ultimately, we want long-term solutions. So my apologies, it looks like there's a little delay between my slides. That's just part of the internet connection. Like I said, it's a collaborative effort. This pilot study involves DNR, the MDH, MPCA, Cottage Grove, and a bunch of the participants from the 14 communities that are impacted. It's a real example of teamwork and something that I guess we're very proud of and happy to have part of our workload. Cottage Grove, let's talk about them a little bit more specifically. Population is 38,000 folks. Drinking water source is groundwater from 12 wells. Prior to the contamination, all that was needed was chlorine and fluoride addition into the groundwater. The water is very good, sans PFAS. But we were able to get now 3 interim treatment systems put in line that buys us time. And now the next part of our study is to go and compare ion exchange to GAC. And as we established our experimental plan for this, we decided to compare 2 leading NSF certified ion exchange resins with the NSF certified GAC, the same GAC that's being used in those interim facilities, so that we have an apples to apples comparison. Some of the supporting goals are that the Department of Health they completely expect new technologies to be presented to them. They don't currently have guidelines, So through our process of getting this ion exchange pilot in place, they're able to start to establish those guidelines and build a policy for future proposed technologies. We also are going to provide the state with some high-level cost estimates and comparisons, because the economics of these two sorbents is very important. For example, GAC, as you can see in this photo, is the column on the right. It's much larger because of the greater empty bed contact time. Ion exchange is a shorter empty bed contact time. GAC is much less expensive to buy the material. Ion exchange is much more expensive for each little cubic foot or pound of material. The differences are, though, that with the smaller footprint required for ion exchange, we can build a smaller facility. So you really have to focus on the economics to find out which of these is more cost effective. Okay. Here's a little closer look at the pilot, some 3 different views. Like I said, we established an experimental plan. One of the other key facets of this study is that we were able to secure Johns Hopkins University through an alliance with Stantec to conduct all of our analysis for the PFAS substances. That's a real key advantage. It's a research laboratory, and they're able to turn around the testing in 4 days compared to, say, a commercial lab, which would take more like 3 to 4 weeks. And so we're happy to have them on the team. This is a better diagram of what we're doing. So with the pilot, we're taking in this opportunity, we're taking water from the wells, storing it in a large 500-gallon plastic tank, and then we're running that water through GAC columns from top flow to bottom, like I talked about earlier, through GAC and 2 leading ion exchange resins over here on the right. As a twist on the study, we're taking, with 2 other additional columns, we're taking effluent from the GAC and running that through the same 2 ion exchange resins to see what impact that might have. Essentially, we're dual treating this water stream, and we're going to compare that to these others, which are being directly compared. Granted, it's not a fair comparison because we know that the effluent from these 2 is essentially getting dual treatment. Okay, so not to belabor this, I just wanted to point out that the empty bed contact time differences for the ion exchange, 2.5 minutes. For GAC, it's 10 minutes. So there's a factor of 4 involved here. And then we are looking at a Dow resin and also a Pure Light resin for comparison. And then not all GAC is created equally either. The resin or the GAC that we're using and have used in those interim plants is a Norit Cabot product. It's a 1240 plus acid washed product. There are all kinds of different types of GAC to consider as well. Some are agglomerated, some are acid washed, and so forth. I wanted to point out real quickly, these are the 4 columns again of resin, similar to the diagram I showed you, and then this is the GAC column on the right. To point out at this slide is the ports. So we installed these sample taps, if you will, at different levels throughout the media beds so that we can get an idea using shorter empty bed contact times of how the removal performance is progressing. So for example, with this port 1 on a 2.5 minute empty bed contact time, port 1 at about 1/3 of the way through is showing a 0.63 empty bed contact time. And so that gives us an idea of what we can expect later on as we get water that's flowing all the way through the 2.5 minutes. And we'll show you more about this in a moment. Like I mentioned, we don't have to belabor, but this was the Johns Hopkins University Alliance differentiator, the bullet on the bottom, 3 to 4 day turnaround. That's very important to us. We have had some issues as we start up the pilot and operate it. It's been in operation for 1.5 years now. We've had different things happen where if we didn't know the results within a 3 or 4 day time, we had to wait 3 or 4 weeks. We would have wasted essentially 3 or 4 weeks of study. So having that turnaround is very important. Some of the early observations, this is kind of the bonus part for you folks. With the pilot, we're finding iron and manganese both are a key complexing issue with the ion exchange resin particularly. We're also finding that PFBA breaks through both ion exchange and the GAC relatively quickly. There was hopes that the ion exchange, and it does do better on some of the shorter chain, but PFBA, one of the shortest chain substances, breaks through both quite readily. So on the subject of iron fouling, what this chart is showing you is differential pressure compared to days of operation. And what we're looking at is in the initial 2 weeks of operation of this pilot, we found that the filters, particularly the blue and yellow, which represent the ion exchange resins, 1 and 2, those had a direct and a very immediate effect from something that caused the differential pressure to rise. As we dug into the issue, we found that it was iron in the water, very low concentrations of iron in Cottage Grove's water at 0.14 to 0.2 milligrams per liter. But it caused this almost blinding of the resin right out of the gate. So once we changed that out and put in some pre-treatment, we used a berm media for this. You can see how the differential pressure stabilized as we expected. As the study progressed to 100 days, we started seeing a rapid increase in differential pressure again. And what we discovered is that berm media was breaking down and getting exhausted itself. So we needed to go through some iterations, and we tried a different type of media called Phylox. This is a media that is a manganese dioxide substance that it performs a little bit better than the berm. You can see the results here, how we were able to get more stabilized results for a longer period of time, about 200 days. But as it turns out, that media is also now, just as we speak, starting to, I think, break down, and we're going to need to replace that Phylox very shortly. This is current as of May of this year, so this month. Bring home some pictures of what's happening. Hopefully it's visible on your screens, but the column on the left shows flocks of iron building up and blinding off the ion exchange resin that's taking water directly from the storage tank. The column on the right is the resin that's essentially being pre-treated by the GAC. So the iron is being captured in the GAC, and the effluent from that is coming onto this column, and you don't see any iron buildup. Very clearly, we have an iron issue. The next slide illustrates the pre-filtration cartridges that we started using. It's like coffee grounds compared to a clean filter there on the right. And so we implemented that cartridge filter upstream of the pilot, and it's a 1 micron filter. We started with a 5 micron. That didn't cut it. So let's get into some more specific test results. I want to point out with this slide simply that we are testing for 32 compounds. These are typical compounds that are being looked at using EPA methods. And so with the state of Minnesota, there are 7 compounds of key interest that they use to create what they're calling an index. But we're looking at these compounds, 32 of them, ranging from C3, that's 3 carbons to 9 carbons, for both what we have here with PFCAs are the carboxylic acids compared to the sulfonic acids. And so you start to see how each water quality is different in this lower chart. In the case of Cottage Grove, the majority of the substances that contribute to the water that's coming out of the GAC is PFBA. We also have contributions from PFPRA, propanoic acid, which we'll talk about here in a bit. Here's the results. What we have on the top column is the raw water. Like I mentioned at the beginning, PFBA is a very high level of concentration in our water, but the good news is it's a short chain compound, and so Minnesota allows more of this in the health index. These 7 compounds are the compounds of interest for Minnesota, and that they do is they combine these into a health index, and if that index is greater than 1, then that's considered non-compliant. Here are the results of concentrations coming through the effluent of GAC and then the 2 ion exchange resins, and then the 2 ion exchange resins that are receiving effluent from the GAC are IX1 and 2. And what you can see here, if we use PFBA as kind of a indicator compound, if you will, PFBA is breaking through and actually higher in concentration in the effluent for all 4 of these different regime that we're testing. And the reason is that there's transformation of some of the other substances can transform and break down and show up as PFBA in the concentration and the testing. And there also could be some desorption taking place where some of the PFBA that's been attached to the GAC or the IX is getting kicked off and then being picked up in the effluent. Of key importance, Pfas and PFOA, we don't have a lot of that in the water quality here in Cottage Grove, but the results are we're getting very good removals. The next slide shows the runs through the interim treatment vessels. Those are the full scale vessels that I showed you a photo of earlier. You can see that with the exception of PFBA down here in the bottom row, we're getting nearly 100% removal of the other key substances of concern, PFBA being the exception. But as you recall from that first slide, we allow a lot more PFBA in the effluent water because of that short chain nature, the lack of bioaccumulation. So here's the other well that was being treated in Inver Grove or Cottage Grove, and we're getting almost 100% removal in most of these, and very good removal still at PFBA. This is a little breakdown of the health index that I mentioned earlier. It's a bit confusing, so I'm not going to belabor it. But as we decrease the health-based values, as the Department of Health changes their perspectives in the study of the toxicology of these substances, they will change the health-based values as they gain more understanding. And so as those values change, it affects the overall index. The index is a summation of these 7 contributing substances. These are the substances that, for Minnesota anyway, they've decided are important in terms of human health. And so as we change or decrease one of these health-based values, in the denominator, it has an increase on the effect. It contributes a greater amount to the overall index and can create a non-compliance. So let's talk about more specifically, perhaps of your interest, is how how the results are showing up in our study. We've got GAC and the 4 ion exchange columns listed across the top here. The top charts are the carboxylic acids. The bottom charts are the sulfonic acids. The key I want to point out here is that you can see that the steeper these curves, the more quickly that the substances are breaking through. And so when it comes to, these are the substances being looked at, there are 13 of them here. As we look at GAC compared to the ion exchange columns, particularly the 2 that are receiving direct flow of water, which is IX3 and 4. When it comes to the carboxylic acids on the top, the slope of the GAC is actually a little more gradual than some of these for substances such as PFPEA, PFBA, and PFPRA. What that means is that for those certain substances, the carboxylics in general, GAC is performing slightly better than the ion exchange. On the contrary, when we look at the sulfonic acids, which is the substances generally that end with an S, those are the sulfonic acids. So things like PFOS, there's a very distinct advantage in ion exchange resins 3 and 4 compared to GAC for the sulfonic acids. The importance of this is that as we try to come up with solutions for these municipalities, we need to be mindful of what we're trying to remove. And depending on what those substances are in their drinking water supplies, it may change your decision making on what type of sorbent to use. And very much like other things, we're trying to really focus and improve and tailor our treatment regime to match the given water quality issues. Here's another way of viewing the results. So the colored portion shows the contributing amounts of these substances to the health index as Minnesota evaluates it. So with GAC, the majority of what's contributing to the health index is PFBA. There's a little bit more of these other PFBS, PFHXS, Pfos, and PFOA in the GAC. Ion exchange 1 and 2, these are the two that are getting essentially dual treated, so that's not a fair race. We don't see much of anything except PFBA there. But the IX3 and 4, this really illustrates how some of those PFOA, the carboxylic acids, are starting to break through quicker through the ion exchange resin than the GAC, and it's depicted with color here a little more clearly. So now if we look at the concentration of these chemicals coming through versus the health index, before we were looking at health index, now we're looking at concentrations per bed volume. And so we're starting to see the GAC is performing about, it's very similar in concentration to the ion exchange resins, perhaps a little bit better on the carboxylics, like I said, and then the sulfonic acids, we definitely have breakthrough concentrations in the GAC, whereas the concentrations of breakthrough in the ion exchange resins is much less, and it's illustrated there. So likewise, now we're switching into looking at the first port. I pointed out the port of the ion exchange columns. That first port, so we're looking at just a partial empty bed contact time. Things are breaking through the GAC much faster than they are the IX columns. But we are seeing those carboxylic acids breaking through at the port 1 as would be expected. So another tool in our toolbox, as we're looking at this pilot study, we're thinking about the duration of time to gather results. That pilot's already been running for a year, and we're getting to a point where we want to try to model what's going to happen. So our team started looking at the available models that are out there. There's a scaled model, there's a taper desorption model, and a composite model. And these models attempt to mimic what the breakthrough curve is going to look like for a given water quality based on a throughput volume of water. What you're seeing, this top curve, is the acknowledgement that there are some transformation breakdowns of Pfas substances that occur, and also some desorption. And so we want a model that can accommodate and account for that transformation and desorption. With our testing with Cottage Grove, we've been able to apply models and tailor them and gather data based on the port 1 coming through the GAC. This is only for GAC so far. We're gathering data on the breakthrough of concentrations of these substances over the course of time. And then we apply our models, and you'll see in the next slide that the models are actually very, very close to tracking with the data. And so we're encouraged by our ability to potentially, and the importance here, to potentially predict with a given water quality how long the GAC will be able to last. So we can start to plan ahead for when we're going to need to exchange the media. And if we do enough testing and compare R square values and chi-square, we're going to be able to develop a curve that for each given water quality for a certain type of sorbent, in this case it's that GAC that's acid washed, we'll be able to develop a curve that's repeatable, and we'll be able to know, hey, if in the case of Minnesota the health index is 1, we'll know that we've got about 100,000 bed volumes before we're going to start to exceed. So that can become very helpful to these municipalities as we're trying to find them solutions for PFAS. Okay, so we have a bunch of different solutions. The topic of this presentation again was to try to find solutions for municipalities to keep them compliant with those ever-changing rules that are out there. And so to summarize what we discussed, based on full scale and pilot scale performance, we know the GAC is a reliable solution for PFAS, at least as it stands with the Minnesota Health Index as our key example. We also know that modeling can help predict sorbent performance, like I just showed you, with a given water quality. And so that's something that can be used to help these municipalities comply. Also, based on pilot study performance, we know that ion exchange is showing as a viable option for providing water compliant, at least in terms of the Minnesota Health Index. Again, recognizing that each state and each region and the US EPA, they're all have different definitions for what compliant means. Also, based on the pilot study performance, GAC followed by ion exchange shows good promise, but essentially we need more time, more bed volumes to really prove out the slope of those breakthrough curves so that we know how that compares directly to these other regime. To truly be fair, we would need to treat compare GAC followed by IX to a GAC, GAC, or an IX, IX lead lag configuration, which we don't currently have accounted for in the pilot. At the end of all this, we need to look at the economics and compare the cost of each of these sorbents, the cost of the facility, and the bed life, the life expectancy for each of them to truly compare the economics of these three options. And with that, I'm almost wrapped up. I'm at 50 minutes. Looks like we have 10 minutes of time left. I thank you very much for your attention, and I'm happy to answer any questions you might have. My contact information, email, and telephone are here on the screen, and I also direct you to a link that's listed here for a YouTube video that was created that explains the pilot that's going on in Cottage Grove.
Great. Thank you so much, Ryan. Now we're going to open up to questions. Like I said earlier, you can type in your question on the left-hand side of your screen, and Ryan will go through those and answer as many as he can. And if not, you can always email him directly with any additional questions you might have. Okay, so let's see. No questions yet, but we'll wait a few minutes and see if they come in.
Yeah, while we wait, one thing I was going to point out on this picture is that this person in the upper right-hand corner, the reason I have this photo is that that's one of the operators in Cottage Grove. And to me, this photo illustrates confidence in the drinking water. He's drinking water that has been tested and gone through their treatment process. So he's really living the commitment to the drinking water quality.
That's awesome. All right, here's your first question. Do you see that, Ryan?
Yeah, how readily does the spent GAC regenerate, or is it disposed? So that's a good question. What has happened with these facilities, these interim facilities, we've gone through one exchange of media. And what happens is, in this case, a company comes in and extracts the media from the vessel, the lead vessel, and then they truck that media off to Darlington, Pennsylvania, which is a company that's set up to put the media into kiln and essentially incinerate it. As we understand it, that media is not being reused for potable use. It may be used for other means, but what they're doing is they're incinerating the media and trying to, I guess, break down the PFAS using incineration. And there's some concern over that. There's evidence that shows that it does in fact break down, but there's also folks out there that would challenge that. We also understand that what they're doing with some of this material is that they are rinsing it and storing the PFAS laden water for future treatment. Okay, the next question that I had, I hope that answers your question. So it's essentially shipped off for proper handling. The next question I see from Carolyn is, does the resin have greater head loss overall compared to GAC? What we found is that the head loss, that was in one of those charts, the head loss is quite comparable. It's actually less for the resin, but it's very dependent upon that iron, that pesky iron and manganese in the water. If we get any of that is not pre-treated, it quickly changes, and the head loss through the IX resin, it climbs and becomes an issue and is higher than the GAC. The next question I see here is from Michael. He was made aware of RO treatment system in which they allow discharge concentrate back to the source water. Actually has secured a permit for this. Have we seen other configurations like that? He was surprised to hear that it was allowed and doesn't expect that it would be commonly allowed. I too have, we are these days, we are being visited by technology providers on a weekly basis. This is a very hot topic, the treatment of Pfas. We had one technology provider that had a reverse osmosis scheme like what you're describing, and it regenerates, it sends the reject water from the RO membrane back to the front and essentially continues to treat that through. So I have seen it. I do not believe that there are any states that are prepared to allow that. I could be wrong, but I do think that type of thinking and that type of technology does have some great value in the future as we refine and learn more about it. I think that things like that the combination of treatments, whether it's RO combined with ion exchange to handle that reject stream, or if we take the reject stream and further through RO membranes, that's the type of thing that we're going to see in the years ahead, as those are going to become more mainstream for potable municipal treatment. And yes, the logic there is that you don't have to get rid of that reject stream that you're concentrating, and eventually we are going to have a very concentrated stream that we will have to do something with, but we may as well get as much processing time and get it as concentrated as possible before moving on. Richard talks about, please define a GAC bed volume. Passing 100,000 bed volumes does not seem like a long period of time if the water feed is constant. So yes, the 100,000 bed, what we have in each of these vessels, that are the ones similar to what's in the picture there, those are 10,000 pound vessels. So they're holding 10,000 pounds of GAC each, and then we're passing water through the lead lag configuration. So the combination of those two empty bed contact times equals about 10 minutes. I think that's what you're getting after there. AAES, is there an intermediate sample port after the GAC that is unaffected by the IXC treatment? Is there an intermediate? There are intermediate sample ports after the GAC. So that we could see, I think what you're asking is, after we go through the GAC and before we go through the ion exchange, can we sample the water and see the effluent results or the concentrations in that stream? And the answer is yes. We have ports and we are monitoring those concentrations so that we can compare them. And I think one thing you might be getting after there is, we're looking for ways to compare that ion exchange, that GAC followed by ion exchange, to the results from just GAC, and what would happen if we had two vessels of GAC. It would be very interesting to be able to compare that. We currently don't have that setup on that particular setup on the pilot skid where we have GAC followed by GAC. only the situation where it's GAC followed by IX. I hope I'm answering your question there. Michael has a question. My understanding is that the reject was not recycled. It was discharged, required NPDES permit, but was allowed. Okay, that ties back to the previous question, I presume. Yeah, so that's very interesting to me. The reject stream, if it's treating PFAS, would have to contain PFAS, and I would be surprised that that's allowed, although apparently in this case it was. There may be some other factors that I'm not quite understanding, but that does seem peculiar to me as well, Michael. Let's see, we have another question. Are the differences in the methods used for removal of spent resins and spent GAC from vessels? Are there differences? This is a good question, and one I don't have the information to answer. We have a meeting set up with this Darlington facility to learn more about what they're doing with the materials that they receive. We quite honestly don't have a firm understanding of all that's happening. We do know that they go through the kilns, like I said, and there's some level of rinsing and storing of materials. But we too would like to learn more about this. And that's why I mentioned is one of the disadvantages of GAC and IX that we don't have that clear understanding of what's happening with those materials. Essentially, we could be passing the PFAS issue to another location. And that's something we don't want to do. Ultimately, we'd love to destroy the PFAS and be done, but the technology just hasn't quite evolved enough yet. Okay, then there's I think a follow-up question came in from Michael that he watched a Calgon webinar. I see we're at the time. I'm gonna stay on here for a little bit, but I watched a Calgon webinar in which they stated regenerated carbon had higher adsorption capacity than virgin carbon. I could see where that could be the case. I would agree. Opening the door to reuse of material. The regen temps were sufficient to destroy the PFOS and PFAS. And unknown was related to air emissions. And that's another very good point. I would say we know, at least through some testing that I've become aware of, that there is PFAS in rainwater. That would beg the question that perhaps air emissions are happening, and that might be a means for the PFAS to get into the rainwater. I'm not declaring that is a fact. I'm just sharing what I have heard. I do think that there is room for regeneration of carbon, and that there's a possibility that it could have higher adsorption. I think that is quite likely, in fact. But this is part of what I was getting at with that kicker aiming at a field goal post that's moving. There are many, many aspects to PFAS that we're still learning about, and it's changing almost on a daily basis. So bear with us as we learn more, but you can rest assured that there are groups like the one I'm part of, and associations like yours, associations like AWWA, and other organizations that are focused on bringing solutions for folks. I see one more question came in. Is the water in the 500-gallon storage tank aerated? No, it is not. And I think what you're getting at there could be, is there some oxidation of iron taking place? And so that was something that we did look at very closely. We looked at the dissolved oxygen and tried to assess what's going on in that tank. And as we discovered, we are finding that iron, there could be a colloidal iron particle size issue that's going on, and that's where that 1 micron filter is coming in quite handy. We're also finding that when we do, like I showed in that graph, when we do remove the iron, the performance of ion exchange is quite good. But without that pretreatment, ion exchange would perhaps be taken off the table, at least for this water quality. And again, if I misinterpreted your question, my apologies. Feel free to email me at the email that's given. I will work to get you an answer. I'd be happy to talk with you all longer. Also have my phone number, and I can get you in touch with other team members as needed. I hope that this was worthwhile for you. I hope that you learned about solutions for municipalities. And I hope that you have a very nice day. Take care.
Thank you so much, Ryan. Thank you, everyone, for the questions. We're going to wrap up for today. And I just want to mention that our next webinar is scheduled for Wednesday, June 9th. We'll have Richard Watson, the CEO of Delaware Solid Waste Authority. He'll be speaking with us on Delaware's unique approach to statewide recycling. The page to register for that webinar will be open as soon as this session ends. Thank you so much, everyone, and have a great day.
Thank you.